This is lesson 16 of the quantum mechanics, a mini lecture series. And I'm going to talk about Bohr's fourth postulate. So I talked about his first three postulates. Number one, electrons move in circular orbits around the nucleus. Postulate two, electrons can only be in specific locations around the nucleus in energy levels. And postulate number three, to move between energy levels, an electron has to either absorb or emit light, a photon, a quantum of electromagnetic radiation. His fourth postulate, angular momentum, is quantized. What does this mean? Well, we know from classical physics, linear, or momentum, which is just linear momentum momentum in a straight line. Momentum of an object is basically an object's mass times its velocity. Basically how hard it is to stop. So it's hard to stop a bullet, let's say, as opposed to a tennis ball, because the bullet's moving at a fast speed. Now, for an object moving in a circular path, like an electron, around a nucleus, it's moving around, its motion is directed towards the center of the atom, which is the nucleus. And as such, its momentum, mv, has to be multiplied by the radius, r, the distance between the electron and the proton, in this case. So am, angular momentum for short, is given the symbol L typically. Physics is just mvr. R is the distance between the electron and proton. M is the mass of the electron. V is the electron's velocity. And this is actually linked to postulate 2, Bohr's second postulate, which states that since the radii of electron shells are quantized means only have very specific values, so must their angular momentum. In other words, nr implies nl. N is an integer. You can only have a whole number of distances r and angular momentum l. N is 1, 2, 3, ... And Bohr also used the result from a paper written by John Nicholson, an English mathematician and physicist, in 1911 on atomic structure. And he's known for quantizing angular momentum in terms of h over 2 pi. These were found in Nicholson's paper in 1911. And the 2 pi is perhaps due to circular motion. That's where it comes from. Think of 2 pi as like one revolution. Think of pi as just 180 degrees. This is in radians. Pi is usually used for radians, measures of angles. 180 degrees, that's in degrees. So 2 pi is double that, which is 360 degrees. Think of a full circle. So h over 2 pi comes into play. So Bohr therefore proposed that angular momentum L, which is just mvr from before, is quantized nh over 2 pi in terms of units h over 2 pi. Where n can be 1, so you can have 1h over 2 pi, 2h over 2 pi, 3h over 2 pi. And larger orbits, so as you go up in number, larger orbits have larger angular momentum, right? So that's Bohr's angular momentum quantization condition. Big words here. Quantization, I'll write it down, means specific. Best way I can define it. Angular momentum has very specific values. It can't be half h over 2 pi or 3/4 h over 2 pi. It can only be fixed whole numbers.